You drop a ball, it hits the ground, it comes back up. You stare at it like it just performed a magic trick. But let's be real, it's not magic, and the ball isn't alive. It's just physics doing its usual thing, forcing objects to obey rules they didn't even agree to. You might think this is simple, but there is a chaotic storm of energy happening in that split second when rubber meets the road. We are going to break down the invisible forces that make bouncing possible, why some balls are lazy and stay on the ground, and why you can't cheat gravity no matter how hard you try. Welcome to Think, where we explain the obvious stuff you never bothered to question. Physics of bouncing balls. Let's start with the basics, because apparently we need to explain why things fall down. You have a ball in your hand, gravity is pulling it toward the center of the earth. Gravity is that invisible bully that keeps you stuck to the couch. When you let go of the ball, gravity accelerates it. It picks up speed, it builds momentum. This movement creates kinetic energy. That is just a fancy term for energy of motion. The ball is moving, so it has energy. The higher you drop it from, the faster it goes, and the more kinetic energy it stores up. It's basically a loaded spring waiting to snap. It is hurtling toward the ground with a singular purpose, completely unaware that the floor has other plans for its immediate future. The stage is set for a collision, and Newton is about to make an appearance. Kinetic energy transformation. So, the ball is flying downward. It has all this kinetic energy. Then, bam, it hits the floor. For a tiny, microscopic fraction of a second, the ball stops moving. It has zero velocity. It is stuck between a rock and a hard place, literally. But energy has to go somewhere. The universe has this strict no refunds policy on energy. It cannot just vanish. So, where does all that motion energy go? It morphs. It transforms into elastic potential energy. This sounds like something from a sci-fi movie, but it is just the energy of shape change. The kinetic energy gets used to squash the ball. The ball flattens out at the bottom, it deforms. It looks like it's doing a weird yoga pose. The energy is now stored inside the squashed material of the ball, waiting to be released. It is a tense moment for the ball, being all squished and stressed out. Elastic collision explained. Now we get to the good part, the actual bounce. This is what scientists call an elastic collision. It sounds technical, but it just means a crash where the objects bounce apart. When the ball is squished against the floor, it is under immense stress. The rubber or material wants to go back to its original shape. It hates being flat. It is desperate to be round again, so it snaps back. This release of tension pushes against the floor. Now, the floor is heavy. The floor is stubborn. It isn't going anywhere. So, the force pushes the ball away instead. This is Newton's third law in action. Every action has an equal and opposite reaction. The ball pushes the floor pushes back, and suddenly the ball is flying upward. It is essentially the floor punting the ball back to where it came from. The elastic potential energy turns back into kinetic energy, and the ball is moving again. Only this time it is going up. Material elasticity properties. But wait, why doesn't a ball of dough bounce? Or why doesn't your phone bounce when you drop it? That is a tragedy, by the way. This all comes down to material elasticity. Some materials are springy. They are elastic. Rubber, for instance, has long chains of molecules that are all tangled up like a plate of spaghetti. When you squash them, they stretch and strain, but they want to curl back up. They snap back efficiently. Other materials, like clay or that phone you just dropped, are plastic. Not plastic like a bottle, but plastic in the physics sense. They are rigid. When they hit the ground, they don't store energy to snap back. They use the energy to break or permanently deform. They hit the ground, they splat, and they stay splatted. The energy is used up, breaking the chemical bonds or making a dent. That is a waste of good kinetic energy. A rubber ball is an overachiever. It recycles the energy. A lump of clay is lazy. It just gives up and sits there. Coefficient of restitution. Here is a term that sounds like a legal settlement from a car accident. The coefficient of restitution. This is just a fancy math number that tells you how bouncy a ball is. It is a scale from 0 to 1. A coefficient of 1 would be a perfect bounce. If you dropped a ball with a 1.0 rating, it would bounce back to the exact height you dropped it from forever. It would never stop. That is impossible because the universe loves entropy and hates perfection. A coefficient of 0 means the ball hits the ground and stops instantly. It has the bounce of a brick. A super ball, those little rubber balls that hit your little brother in the face, has a coefficient around 0.9. It is incredibly efficient. A baseball is lower, maybe around 0.5. This number measures how much energy the ball keeps versus how much it loses as heat or sound. When you hear that loud thwack sound, that is energy escaping the system as noise. The ball literally pays a tax to the atmosphere every time it bounces. Why balls stop bouncing? This brings us to the sad reality of the universe. Why do balls stop bouncing? If energy is conserved, shouldn't that ball just keep going forever? Ideally, yes, in a frictionless vacuum with perfect elastic collisions. But you don't live in a vacuum. Well, maybe you do socially, but physically you don't. In the real world, the ball is fighting air resistance. Every time it moves through the air, it rubs against air molecules, losing a tiny bit of energy. More importantly, the ball isn't perfectly elastic. Every time it squishes and unsquishes, the molecules rub against each other. This friction creates heat. The ball actually gets slightly warmer every time it bounces. That heat is energy leaking out. Sound is energy leaking out. Eventually, the ball runs out of juice. It doesn't have enough energy to push itself off the ground anymore. It gives up. It succumbs to gravity and rolls under the couch, where it will remain until you move out. This is the law of entropy, the slow march toward disorder and stillness. Conservation of energy examples. To wrap your head around this, look at a trampoline. It is the same principle, but easier to see. You jump on it, the mat goes down. The springs stretch, the springs store the energy. The springs snap back, launching you into the air. A ball is just a trampoline that carries its own mat and springs with it. It is a self-contained bouncing machine. The air inside a basketball acts like a spring too. When the ball hits, the air compresses, the pressure goes up. The air wants to expand, so it pushes the ball back up. If you don't pump up your basketball, it's a soft, sad sack that barely leaves the ground. No air pressure means no internal spring. It's all connected. Energy is moving, changing forms, and fighting gravity until it finally loses the fight. So there you have it. Balls bounce because they are elastic objects that store kinetic energy when they hit the ground and release it to push themselves back up. It is a cycle of squishing, snapping, and flying, all governed by the laws of physics and the stubbornness of the floor. Next time you bounce a ball, remember you are witnessing a complex transfer of energy. Or just keep staring at it blankly. That works too. If you actually learned something from this chaotic explanation, go ahead and smash that subscribe button. It helps the channel more than you think. This is Think. Now go do something else.